Good morning. This is Dr. N. Ramya, Assistant Professor from Civil Engineering Department. Here I am going to teach about laminar flow through parallel plates in hydraulic engineering. So here in previous sessions we have discussed what is laminar flow and what is turbulent flow and what is the difference between laminar flow and turbulent flow, and also we have learned the laminar flow through circular pipe derivation also. Now here is the second derivation, that is laminar flow between two parallel plates. Laminar flow between two parallel plates. The flow is laminar flow. So now we are deriving the laminar flow between the parallel plates. So here flow between two parallel plates, for deriving this the assumptions are three assumptions, that is steady, the flow should be steady, and it should be incompressible, and it should be fully developed flow. Inside the pipe, the flow should be inside the pipe. When you're supposed to place two parallel plates, in that two parallel plates, the flow should be steady, flow should be there, and also incompressible flow, and the flow should be fully developed. Flow should move in between the parallel plates. So, and here another assumption is no slip condition at the plates. Here there should be no slip condition, means there should act some friction. There should act some frictional resistance. There should be some frictional resistance due to the plates. And here negligible body forces. These three are the assumptions to derive the laminar flow between two parallel plates. Right. Now we are saying, let us considering the laminar flow between two parallel plates located at a distance. The distance between two parallel plates is B. The distance between two parallel plates is B, apart such that the lower plate and the upper plate, both the plates are at rest condition. Both plates are at rest condition. That is nothing but stationary. Both the plates are stationary, right? And the distance between these two plates is B. A small rectangular element of fluid of length dx, and the thickness of the plate element is dy, and the unit width is considered as a free body. And for this we are taking a small element to derive the derivation between the two parallel plates, flow between the two parallel plates. So here we require a small element, which is the length of the element is dx, and the width of the thickness is dy, and width is unit width. Unit width is 1. Right? This is what the rectangular element which we considered to derive the laminar flow between two parallel plates. So here is the image. Both the plates are at stationary, that is a rest condition. Here is the plate, here is the element, small element, that is we are taking in x direction, that distance is dx, and the thickness of this element in y direction, that is dy, and the width in third direction, it is unit width, that is 1 unit width. So we are taking two-dimensional image here, so that's why we are taking only dx and dy, right? So here, if to this element, there are 4 forces are acting surrounding. One is at left hand side, and other is at right hand side, and one is lower side, and other is upper side. Here 4 forces are acting on the small element. Right? On the left hand side, the force acting is P into dy. P into the distance dy. And here at the lower side, now we see first right side. So the right side is P into dy plus this, complete the difference, dou P by dou X into dx into dy, differential element at right hand side. Now lower side it is tau into dx, shear stress into dx, and on upper side again here tau into dx plus dou tau by dou y into dy into dx. This is the upper side. These are the four forces acting on the small element between the two stationary plates. So here the tau is already we know that is shear stress which is acting on a face BC. Then the shear stress on the face AD will be tau plus dou tau by dou x. So here if you see here at lower side it is tau and the upper side it is tau plus dou t by dou y, right? Dou t by dou y. If the width of the element in the direction to the paper is unity, then the force acting on the fluid element shall be as follows. Here we are taking width as a unit, so that's why we are taking these are the values, that is width we are taking 1. So the pressure force is what? P into here delta y, here written, so we are writing here delta y, right? Again at the pressure force, this is on left hand side and this is a right hand side, that is the pressure force is on right hand side, it is P plus dou P by dou X into delta X into delta Y into dy, because we are considering here 1 also, that is unit width also we are considering for face CD, right? Here it is AB and here CD, right? So here AB it is P plus P into delta Y, on left hand side on face CD it is dou P by dou P plus dou P by dou X into delta X into delta Y into 1, that is your force acting on a face CD on right hand side. CD is right hand side. So here another again here upper, this is it is lower, and here it is upper. So the lower force, the shear stress is tau into delta X and the shear force on upper side is tau plus dou tau by delta V into dx into 1 on face AD and here this on face BC. So these are the four forces acting on the small element, rectangular element. So here already we have assumed that the flow is steady and the flow is uniform, right? And there is no acceleration. So here the resultant force which are acting on the small element in the direction of flow is 0. For the small element, the resultant force in the direction of flow is equal to 0. So what are the forces acting on the small element? We are equating it to 0. That is here, this is a left side and this is your right side force, and here is the lower one, this is your upper one, right? These are the four forces acting on the small element that we are equating to 0, right? So here what we are getting, when you do it simplify here, you will get minus dou P by dou X into delta X into delta Y, right? And another one is what? Dou tau by dou X into dy at delta Y into delta X is equal to 0. This is the term, when you simplify this you will get this term, because some terms will get cancellation, right? So here this is what we got at the final one. So when you divide this with delta X into delta Y, when you divide this with delta X into delta Y, you will get minus dou p by dou x plus dou tau by dou y is equal to 0. So this I'm taking on the right hand side, so that the equation is becoming dou p by dou x is equal to dou tau by dou y. So here next we are deriving here first velocity distribution in the small element, right? So here this is what a generalized one. From these equation we are getting a we are taking out a velocity, how velocity is distributing, and what is a value of u and what is u max, we'll say now, right? So here is the, from according to Newton's law of viscosity, for laminar flow it is, already we know tau is equal to mu into dou u by dou x, right? So here dou u by dou y here terms, right? Mu into dou u by dou y, right? So here what I am doing, in place of tau, I am writing mu into dou u by dou y. This term I am writing in place of tau here. This is what complete it is, tau. So when you differentiate this, you will get mu into dou square. This dou square mu by dou y square, right? So dou p by dou x is equal to mu into this. We are not differentiating here, directly we are getting that dou into dou u becoming dou square u, and here dou y into dou y becoming dou y square, right? So dou square u by dou y square, that is equal to 1 by mu dou p by dou x. This complete term I am taking on left hand side and all other terms on right hand side, so that the equation is becoming dou square u by dou y square is equal to 1 by mu dou p by dou x. This is what the equation you are getting. After getting this, we are integrating with respect to y here. After getting this equation, we are integrating with respect to y. So that we get this, when you integrate this equation, you will get dou u by dou y is equal to 1 by mu into dou p by dou x y plus cy1. So the differentiation will become dou u by integration will become dou u by dou y is equal to 1 by mu, here dou p by dou x is same, into differentiation of 1 is y. Right? So that's why 1 by mu dou p by dou x into y plus c1. And what I am doing here, again I am integrating, because here it is dou square. So again I am integrating here to get u. So here when you integrate this, you will get u, dou u by dou y will become u, that is equal to 1 by mu dou p by dou x into y. Integration of y is y square by 2. So y square by 2 plus c1 into y plus c2, because we are integrating second time. This is second time integration. Here is the first time integration. You will get plus c1. When you do it again second time, you will get c1 y plus c2. Clear? Here and here both the c1 and c2 are constants. We have to find out what is c1 and what is c2 by giving some boundary conditions, right? By giving some boundary conditions, that is first. Here this is your parallel plates and the flow is moving in between these two plates. Yes, so this is the y direction, right? So this is y and here is the x, right? So this is y, this is x. So at this point the velocity is 0. Here also already we have learned that at the boundaries the velocity is 0 due to the frictional resistance acting at the boundaries, right? So here the velocity is 0 and the velocity is maximum at the center, right? Velocity is maximum at the center. So here at y is equal to two condition. First condition it at y is equal to 0, your velocity is 0 because of the resistance occurred at the boundary. This is one condition. And second condition is at y is equal to t. We are calling the distance between these two t. First I have said UB, but here T is written. Okay, let it be, no problem. So here I am taking our value. Distance between these two is T. Right? When the distance, when your y is becoming your T, then what happens to your velocity? It is 0, because due to the boundary, due to the which is offering resistance. Right? That's why your velocity is 0 at y is equal to T. Y is equal to 0 is also velocity is 0, and at y is equal to T also velocity is 0. By applying these two boundary conditions to the equation, to the above equation which we got when we integrated both two times, right? So that equation we are applying these boundary conditions. First condition is what? At y is equal to 0, u is 0. This is condition number 1. So in place of y we are giving all zeros, and in place of u also we are giving a value 0. Right? So what is the equation here? We got C2, that is equal to 0. C2 will become a 0. Right? So here this is the equation. So we are writing here another boundary condition. This is boundary condition 2. Right? So when you apply this boundary condition 2, that is y u is equal to 0, here is the u, that is 0, and in place of y you are writing t square plus c1 into y. In y place we are writing here t, and c2 already we got, that is in from previous, that c2 is 0. That's why I'm directly writing here c2 is 0. Right? So when you simplify it, you will get c1 is equal to, you taking out c1 outside, because here we need c1 and c2 values. Right? So here c1 value I am writing out, c1 is equal to minus 1 by mu dou p by dou x t square by 2t, that is equal to, why? Because it is plus here. When you move this complete to other side, you will get negative side, right? So c1 is negative 1, that is minus 1 by mu dou p by dou x t square by 2t. So that will becoming, when you t, so 1 by 2 mu dou p by dou x into t. This is what I got from, this is what is the value of C1. C2 value is 0, C1 value is this C1 value. Right? So after getting C1 value, we have to substitute these two C1 and C2 value in the above equation. Right? So this is what a C1 value, and at C2 it is 0. That's why here no value we have written. Right? So this is what u is equal to 1 by 2 mu dou p by dou x into y square plus y into minus 2 by 1 by 2 mu into dou p by dou x into t, plus c2 is 0. Right? This is what the equation is. So from this above, we are getting final one as mu is equal to minus 2 mu dou p by dou x into this one ty minus y square. So here the value, here the u value is ty minus y square into dou p by dou x into 1 by 2 mu. This is what your velocity is. Your velocity is. So we got here velocity. So now we are calculating the shear stress. So shear stress already we know mu across a section varies from t, as dou p by dou x across section is constant. Right? So here this at the boundaries the velocity is 0, and at middle it is velocity is maximum. Right? So here the velocity profile is parabolic, right? And here the shear stress is maximum at the boundaries, and shear stress is minimum at the center. Boundaries it is maximum, at boundaries it is maximum, and at center it is 0. But here velocity is maximum at the center and velocity is 0 at the boundaries. Right? So here we got u value. We have to find here u max. What is u max now? So already we know that u max is at the center. So the distance between two parallel plates we are denoting with t. right? So the maximum velocity is at the half of the distance between the parallel plates. So t by 2. At t by 2, you see the maximum velocity. So where y is equal to t by 2, your u will become u maximum. Velocity is maximum. So here also in place of u, writing u max, that is equal to 1 by 2 mu dou p by dou x, and in place of y, the equation what we have seen here, ty minus y square, right? So here in place of y, t by 2, in place of y, t by 2. So this is the equation for your maximum velocity, right? So 1 minus 2 mu into dou p by dou x, here it is becoming t square by 2 minus t square by 4. At last, t square by 2 minus t square by 4. At last, your equation is becoming minus 1 by 8 mu into dou p by dou x into t square. Into t square. This is the maximum velocity equation. 1 minus 1 by 2 mu dou p by dou x t square by 4. Yes, t square by 4. So I am taking this t square by 4 to here. So 8 mu. 2 into 4 is 8 mu. So this is what your maximum velocity is. So the average velocity. Now we have to calculate average. First we have seen what is u. Yes, after that what is maximum velocity for a small given element, rectangular element. Right, that also we have found. And next we have to find out what is average velocity u bar. Yes, u bar is obtained by dividing the discharge and the area. What is discharge? Discharge is area into velocity. So here we need u maximum. So u maximum is equal to discharge by area. So that you will get average velocity. So here discharge. In between the parallel plates is complete Q. I need only a small element discharge. So the small element discharge is dq. I don't need complete what is the flow moving in between two plates. I need only the small element which we are deriving for. The small rectangular element, that is small rectangular element is taking a discharge of dq. Only this dq discharge is moving in a small strip, small rectangular element. That is dx in between distance dx, and here in between in thickness is dy. This the discharge carrying the small element is dq. Right? So here dq velocity into area, discharge already have written. So here dq velocity is already we have derived. Normal velocity, that is 1 by 2 mu dou p by dou x ty minus t square. Here this is u, normal u, into area of this strip is how much? This distance dx into unit width. That's why I'm writing here dy. Height carrying discharge, 1 minute. Yes, this is what your strip is. This is dy. So it is carrying, it is moving in this direction. So I need a distance. Area is dy and the width of this is 1. Right? That is area. If we consider this dx also, then it will become volume. Here I need area. So the area is dy into width of this rectangular element. Right? So dy into 1. So here I am writing dy into 1. So to differentiate, again I am integrating here. Dx integrating. So that what I am getting here? Q. Integrating. Q is equal to here. Integrating dx. So here integration. Here it is 0 and thickness is y. Maximum limit. The limit I am taking in between 0 to t. So 0 to t, that is equal to minus 1 by 2 mu dou p by dou x into ty minus y square into dy. Right? So here minus 1 by 2 mu dou p by dou x ty square. This will becoming t y square by 2. This is becoming 2 plus 1 by 3. So ty square by 2 minus y cube by 3. Right? So here in limits, that is 0 to t. So in place of y, I am writing t. So here y into t square is becoming t cube. Here y cube is becoming t cube. Right? So the next, it is 1 by 2 mu dou p by dou x t cube by 6. 6 into 2, it becoming 12. So what is your what is your discharge q is minus 1 by 2 mu dou p by dou x into t cube, the distance between the parallel plates. Right? So here mu is equal to q by a, q is this, and area is t into 1. Now this area we are taking t into 1 unit width. Now we are applying this small strip to complete parallel in between plates, right? So t into 1. So what it will becoming u average is minus 1 by 2 mu 12 mu dou p by dou x into t square. Here t is getting cancelled, it will become t square, right? So t square. So here u bar is this. This is your velocity average minus 1 by 12 mu dou p by dou x into t square, right? So now next, ratio between u maximum to u average. What is the ratio between u max to u average? So here u max is 1 by 8 mu into dou p by dou x into t square, and here u bar is minus 1 by 12 mu dou p by dou x into t square, right? So it is becoming 12 by 8. All will getting cancelled. And the equation is becoming 12 by 8. So that is 3 by 2. 3 by 2. That is 1.5. So the maximum velocity is 1.5 of average velocity. So the maximum velocity is 1.5 of your average velocity. This is important one. Now next, we got average velocity. Yes, that is what? Minus 1 by 12 mu into dou p by dou x into t square. So now here I am calculating what is pressure drop. Pressure drop or pressure head, right? So here dou p by dou x, I need this p. So that's why I'm writing on left hand side dou p by dou x, that is equal to minus 12 mu u bar by t square. This is what your equation is. Because here we are taking this on left hand side because to calculate this, right? So again I'm integrating this pressure in x direction with respect to x, so that your equation is becoming 1 to 2, because section 1 and section 2 here, when you have, if you want to calculate a pressure drop, you need a section in between. What is the pressure drop between the small distance from section 1 to section 2? We can calculate the pressure drop between these two sections. So here we need two sections. One is section at section 1 and here section 2 at some distances, right? So here section 1 to 2 dou p, that is equal to integration of 1 to minus 12 mu u bar by t square into dx. So here section 1, section 2, section 2. So I need a pressure 1 at pressure 2. Section 1 pressure 1 minus section 2 pressure 2, P1 minus P2. That is equal to minus 12 mu u bar by t square into x1 minus x2. At here the distance x1, the distance is x2, right? The distance from here it is x1 and here it is x2, right? So here minus 12 mu u bar by t square into q square minus q1. Q square x2 minus x1. The distance between these two is x2 minus x1 is the distance between the section 1 and 2. So x2 minus x1 I'm writing here. Right? So here P1 minus P2, that is equal to 12 mu u bar by T square. The distance between these two is L. The distance between those section 1 and section 2, x2 minus x1 is, I'm notating this with length L. So I'm writing here in place of x2 minus x1 directly L. So the pressure drop is how much? 12 mu u bar into L by T square. So this is your equation of your head loss. Frictional head loss is the drop of pressure head. Then your HF will become, head loss will become P1 minus P2 by rho G, head, pressure head. We are calling, that's why here we are writing rho G in denominator. So that will become your pressure head. So here P1 minus P2 by rho G, that is equal to 12 mu u bar L by rho G into T square. The distance between these two is two plates. Right? This is what your pressure head is. Pressure head in between two parallel plates. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.